Thank you, Dr. Pawan. You're very kind. Actually, as you said, in fact, it's not 5 years, 6 years ago we started. So, this is in fact the phrase self-offloading is Dr. Pawan's. We had a crazy idea and we were talking, and then that crazy idea turned into what I will be presenting now. We added the word dynamic a little later. So, dynamic self-offloading footwear. This is actually funded by Rajiv Gandhi University of Health Sciences, the state government health science department. They funded this project where Dr. Pawan and I worked, and the two key people who have underlined here, my PhD student Priyabrat Maharana is sitting somewhere there, and then Jyoti Sonavane is in the US now doing her higher studies, PhD. And I also have 3 other students sitting there, Ahmad Shaikh, Ahmad, get up and see this, Nikhil, Muralidhar, and Chinmayi Prasad. They are still working on it. So, what I presented mostly the work of Priyabrat Maharana and Jyoti Sonavane, and Sharat Gowda's name. Actually, we had this grant allowed us to have one person working with Dr. Pawan at KIER, Karnataka Institute of Endocrinology and Research. Sharat actually helped us collect data from patients. And right now, the work is also being supported by the Principal Scientific Advisors Office, and we have a BEST cluster that is called Bengaluru Science and Technology Cluster. They will be making a short presentation little later. So, in the morning I talked about we are going to have our own hospital and Portugal Medical School. We actually like it because without that we are working with a lot of clinicians from our group. We call our lab M2D2, kind of futuristic R2D2. One of them is where we work with gastroenterologists, Professor Dr. Nageshwar Reddy in Hyderabad, AAG hospitals, through which we developed this endoscopy simulator. That is now a company called Mimic. It is funded by our Robert Bosch Center for Cyber-Physical Systems. And then there is other one which was based on the PhD thesis of my student, my former student Dr. Santosh Bhargav. This is where he worked with, after he left the lab, he worked with embryologists to found this company called Sperm. That is a portmanteau word for sperm and ovum, where they do this intracytoplasmic cell injection. Our contribution, our lab contribution, little circle at the bottom, the orange circle, a yellow circle, where we have a compliant mechanism that can hold egg cell that you can see. If I can get the mouse, laser pointer, here. So, over here what you see the egg cell, and then through this pipette introduce a sperm and fertilize, and they have a couple of, actually one baby is already born with that technology, and that is a company founded in Bangalore and they are working on it. And the third one that we have, where we work with geriatricians, our next door neighbor MS Ramaya, Dr. Medha Rao initiated this project. We have developed a chair, that is a company called TransLead now in incubated in IASC, and this chair is special, it is all mechanical. So, here instead of just normal chair will be like that, other chair you can swing like this, but this one not only swings but also goes up and down. It is a responsive mechanism, that is the same person can sit in different ways that is comfortable for her or him. And with that 4 things that we did with clinicians, so we have this fourth one, I call it clinical plus. This plus is actually clinical plus because we are working with clinicians, and that is this footwear that all of you are very familiar with. We have been already working with for many years with Dr. Pawan, and very soon we are going to work with Dr. Paul Graham, and of course Sanjay Sharma has been with us providing the other things, and we will be working with them also. Okay, so first you have to bear with a little bit of mechanics. I am a mechanical engineer, whatever I and my students are doing actually is mechanics, they find a clinical angle, right. So, since professors always have a prerogative, and it is after lunch many sessions are there, it is little warm. So, what I am going to say is the prerogative is professors can ask questions at the end. So, I have a question for you at the end, so that you can all pay attention. Okay, sure. Our thing, so I will make it easy, this nonlinear mechanics, by giving you actually our design here comes from a little lid that some of you might have seen. I will pass it around so you can play with it, so that you can keep yourself awake. This is a what we call a bistable thing. It actually makes noise without the mic, right? You can see it. I will actually pass it around. Dr. Pawan has seen it before. So you can play with it. I want it back. These are all my ties. Yeah. So if you actually look at that, it's a bistable shell. That's what we call it. So if you look at the force versus displacement, force you have on the y-axis, displacement you have on the x-axis. The curve goes like that. Anything that does not go like a straight line, which is linear, when it goes like this, things become interesting, and that's what we are going to talk about. So if this shell is there like that, when you get it, you will do that. If you press it a little bit, after certain force is applied, it actually will be the intermediate state, in between state, as shown by the red one. It goes to the other state where the curvature, which is like top like this, becomes bottom, changes its curvature, sign of curvature. So what is like a dome becomes like a cup, right? That is bistability, and that's the one that I am passing it around. Now what we have done is, in that one, we actually take a curve of it, okay? That's a shell. Now I am taking just a curve of it, sectioning and looking at that thing, and that's what we are using. Maybe by that now you already got an idea of what we are doing for offloading the plantar pressure. So if you have this arch like this, when there is pressure here or force, if it were to be just rotating this piece here, if I simply rotate about this point, it would have been like that. But actually what happens, these two are connected, so it has to deform a little bit. So this has no stress in the beginning, stress meaning that there is force and some strain energy will be there in it, where it is, whenever apply force on something, there will be what we call strain energy in it. In the beginning there is no force, no strain energy, no stress, okay. And now when you press the force, it will stay there, even if you remove the force, like the shell that I am going to be, you are going to get soon to play with. Initially there is no force, it stays there, and then you press on it, it goes other state, again there is no force, it stays there, but it is stressed a little bit, okay. So in between, if I look at it this way, the force versus displacement go non-linearly like this. This we call a stable equilibrium, no force. And there is another stable equilibrium, force is 0 again. In between also there is force 0, but you call it unstable, it cannot stay there. You remove the force, it goes to either this place or that place. In fact, our eyeglass frames have that, right. I am here, it is going to come back here. If I am there, it comes back here. In between, I can very carefully I have to say, I can stay it there, but little push will take it that side or that side. It is a bistable one. That is what we are showing with our energy here. Energy is like a valley, it stays there. Imagine like a ball. On another valley, it stays there. The hill, that is unstable point. And in between here, what we see is the curvature change that you are going to see. Top, it becomes bottom like this. In between, there is this little region that I am showing in red, where we have what is called negative stiffness. So stiffness is a property where you apply some force, it try to push you back, like any spring that you are familiar with. They are all positive stiffness springs. Anything that you have, when you push, they are going to push you back. But there are certain springs where you push, they go on their own. That is a negative stiffness. That is, they do not push you back, they take that and move on. That happens here in between, and that is what we are using for offloading purpose. So this is a high speed video of those, one of those arches. Just we are pushing on something. Of course, high speed will slow down. It will play again. So you watch again. It loses contact. So that the little metallic thing we have loses contact, and that is what we are doing for this self-offloading, okay. And again, mechanics will be lasting one more minute if you bear with me. So the way it is deforming, the high speed video you saw, it actually bends in multiple ways. Each of them we call it a mode shape. It can just have this mode, or it can have one wave or two waves, three waves, four waves, infinite waves. We can have a lot of them. We use them as a combination of all of those to model our arch deformation, okay. That is what we do when it goes there. There is some mathematics there. I mean, this afternoon is not for that mathematics, but I hope you got the idea of what is happening here. Negative stiffness, the force, when it exceeds certain value, it will go by itself. You do not have to push it anymore, that goes by itself, because that has the property of negative stiffness. And we can compute certain things at what force it will go off by itself. That is what we call it a switching force. If force exceeds certain value, it will go there. Now we can design these arches for the value of the force. Sometimes some of these arches in practice would not stick to one plane that they are in. If I take an arch, it will not stick to that vertical plane, it actually goes away also. That happens in reality. So, there are some these little arches here that again I will show you, again I will give it to here. So, you can take it and feel it. Sometimes they go like this, instead of bending like this, they actually twist and bend and go like this. So, all those things we have studied, and if I look at one of those curves here, it actually confuses me also, because it goes very complicated force displacement diagrams. So, we studied all that for the sake of designing footwear, and we have also done some more what we call synthetic modeling. That is, if you have some shape and other shape that you want to go, right. So, how are they two related? Okay. There is something more that I have to emphasize now. There is bistability, which takes that shape and then stable the other one. The other one called snap through, that is, it goes to the other state, but it is not stable there, it is going to come back, and that is what we are using in the footwear. There are some more equations how we relate one shape to the other shape, so that we can design the arches the way we want for this application. Okay. So, that is just to mathematics show that there is a lot of modeling that went behind. Okay. Now, let me come to the footwear. This is a familiar diagram for you, and so is this. So, there are different ways of offloading that you do. You do contouring, you do some scooping out, create pockets to protect the region that is vulnerable for ulcers and so forth. And in the morning, Dr. Armstrong showed this slide, which you are familiar with, when you have these little actuators, and there are sensors which sense the pressure that that particular region is experiencing. Then the actuator will be turned on. So, you need a microprocessor, you need a battery, all of this put together, the price will be over there. Okay. So, we are trying to do the same thing. There is sensing, actuation, processing happens mechanically, you don't need battery, it is just self-offloading, that is your way of walking itself will offload, and that too dynamically. So, this little video will illustrate the technique, because I showed the arches now, it will pass there. When the heel strike happens, that went a little bit. It is just a artistic rendering that one of my students did, couple of my students did. But what happens here is this, one single arc that I am passing around, how it loses contact, and high speed video below, right, it just loses contact. It all happens very quickly, you know how quickly it happens when we walk, and we can design these things. The graphs there show you how that offloading, this is a reaction force and this is the time. Reaction force can come down like this quickly and then come back up again if you want, right. That is how we have this snap through, where it just goes there, it is not stable and comes back up again after some time. That switching time and switch back time, both of those we can design the arches for what is needed, and that is how we are doing. And we published with Dr. Pawan a paper in wearable technologies. Wearable technology was talked about in the morning, but this is wearable technology mechanical, there is no electronics, there is no computer software here. Everything is designed into the arch dimensions, and of course, the material that we choose for it. And before we actually designed at KIER, we had about 100 patients. Dr. Pawan helped, and Sharat Gowda took the readings along with Priyabrat and Jyoti, where we had looked at what is the plantar pressure in different regions of the foot, in different phases of gait, you know, heel strike, flat foot, and mid stance, and heel off and toe off, and swing phase. Right, we got an idea in different parts what should be the area, which area will have how much force we should limit, and so forth. The 210 kilopascal being the guideline. So, we took that and started putting these arches in an array fashion, right. Like you have these little pieces, every one of these are arch here, looking at the top view, okay. And of course, dimensions are there, we have calculations, modeling, everything. With that, we could actually design these things. So, these things have arches now, this is the top view, side view, this goes like an insole, and over that is what you saw in the previous slide is actually real shoe, that probably it is here, you can wear and see as well. So, we are 3D printing these arches. This eminently customizable, that is, for a particular patient, if you say this region should have that force, this force, we can put these arches, because we have mechanics calculations to aid us to design all that. We can put that for a particular patient. There are these little plates at the beginning, but now we have many more that we can do. and also on a pressure mat it was tested, not with a patient, but with a student, right, Priyabrat I suppose, this particular video, and we see that there is some offloading, right, I mean reduction in the plantar pressure in different regions of the plantar pressure, and we can see the reduction here. But we have to do a lot more studies, clinical studies to do this. That is where we look forward to working with Dr. Paul Graham as well. So, here just to pictorially to represent qualitatively what is happening, normal footwear, heel strike and other regions we have red high, static offloading that are normally prescribed for patients will be somewhere else, things will be high when you offload in one place. Self-offloading that I just explained to you will reduce the plantar pressure of being red, it will be slightly less, and what I am going to present next is even better. Just like you have transfer ulcers, now we do not want to do transfer ulcers, we want transfer loads. So, can you transfer dynamically one place to another place? For that, maybe by this time you also got the idea. Instead of using one arch, use two arches connected, right. When the force applied here, this comes down, another one goes up, because when you are offloading somewhere, the pressure has to go somewhere else, weight of the person is not going to reduce, right. So, we are actually connecting the arches now, so that when it is offloaded the heel, it will go to the natural arch of the foot. So, just to illustrate again a mechanical device, one goes down, other goes up, and then while you are walking adjusts itself. Now, this array of arches that we have, we are adjusting them so that pressure is selectively redistributed. And these are not bistable, they are all what called snap through, they will not stay, this is bistable of course, the device that is made, but the one that I am passing around are all snap through, meaning they will go to the other side flipping, but then they do not stay there, they come back, and the timing also can be controlled by designing them. And then we are not stopping there, we are now trying to model the foot itself to see that when we design some arches, how well they work. And let me just play with this video. This is finite element simulation, solving partial differential equations, right. So, when we do that, how arches will lose contact sometime, they tilt and go there, just a simulation, and also how do you model the entire foot with the bones and ligaments and tendons and muscles which are modeled like forces. So, here is another simulation, this is what my student Ahmad is doing. In fact, I am presenting for the first time, I should not do it, I think always students should be presenting first, but then we could not contain our excitement to share this with you. Ahmad is here to answer any detailed questions they may ask, right. So, here we are able to model the basically the heel and toe off and heel strike and toe off and so forth, and also get the plantar pressure computationally. I mean, a lot of other people have also modeled it. So, we just kind of redoing it and trying to understand how best we can do it in a simplified way, and we do not go to the detailed bone structure, it is all simplified. For example, a bone like this will become a simple cylinder, a bone like this becomes cylinder with two balls at the ends, but it gives reasonable results, and that is what we find, and complicated other things we can simplify with all of these things now, and then model the cartilage and everything also here in between the bones. So, we can model everything is inside it. Now, we can actually do this, the simulation that I showed, how these arches would go, and we can measure the plantar pressure computationally, and well, this just shows that threshold pressure exceeds, this will lose contact and it will go somewhere else. That is better seen in the kind of images that you are familiar with. Normal plantar pressure would look like this with our arches put in there with a transfer of the force. So, what is high here can be transferred to the middle region. So, we can actually redistribute the thing and can be prescribed for each patient, and we can design these arches because all the calculations are ready. Okay. That is all I had to say, but then I said I will ask a question. Okay. Here is a question. So, when we were thinking about it, couple of my colleagues who saw this, they also got this idea, no, why are you offloading completely? That is, when you just need to lose contact and go down, why can't you keep a threshold pressure? This is something that Nikhil, who is sitting there, has designed a mechanism now, like an arch here, there is another little mechanism that is put there, where we can actually make the pressure limited to that region, asymptotically goes there, it is not going to exceed, in which case we will be offloading only the excess pressure. If it is 210 kilopascal, excess of that we transfer somewhere else, as opposed to what we are currently doing, we are completely losing contact and going there. Which is better is something that maybe you can think about and tell, because you are always used to offloading, right, but now you do not offload everything, offload only the excess pressure. But of course, whatever you think, of course, there is this tangential or shear component that also we have. In fact, the one that is going around, and this is our insole that it is there. I will pass this around also, so you can play with it, and this is just one sorry, I will go there. Yeah. So, instead of doing this, would it be better, or can we compare both of them and then see which is better? Okay, I leave that question to you. Now you can ask me questions. Thank you very much.